Dear student, Assalamu alaikum. Today we will continue the AC analysis of BJT amplifiers. We will continue the modeling of BJT for small AC signals. We have already biased the transistor in our desired mode for a specific configuration. The desired mode was active mode, right? Because we were discussing the application of amplification. So for amplifier design, we have to bias the BJT in active mode. And currently we have selected only a common emitter configuration, right? Because we are applying the input at the base with respect to the emitter, and we are collecting the output at the collector with reference to the emitter. So emitter is behaving as a common terminal for the input and for the output. So this kind of amplifier, BJT based amplifier configuration is called common emitter configuration. So for amplifier design, common emitter configuration should be in the active mode. That is, base to emitter junction should be forward bias and collector to base junction should be reverse bias. So we have done all these things, right? And we have seen the AC equivalent circuit, only AC equivalent circuit, removing the DC, for instance, right? And then again we have collectively seen the overall behavior of the BJT if we have a DC and AC biasing, right? DC biasing and AC signal injection. And we have seen that for both the supplies, the biasing supply and the input signal to be amplified, when work together, the BJT has to behave for the overall, the total voltages and currents. And we have seen that the collector current, the total current would be nothing but a pure AC signal at the biased current, right? And this AC signal is a nonlinear function. So as the DC value, right? And we have seen that for small input signals, for a small input signal, we would be having a small VBE, AC VBE, and for a small, very small, then what value? Then VT. This relation could be of this form, linear form, right? And again, we can see that the AC part is nothing but a factor multiplied by the input AC signal at the base to emitter junction, the input junction, and the factor, the multiplying factor is nothing but our DC biasing. So it means we can change this multiplication factor of input AC signal by biasing the transistor to a desired location, right? So previously we have considered only the maximum undistorted amplification based by amplifier design, right? So we can consider the designed amplification of the AC signal into our DC biasing selection process, right? So we will see this later on, right? Because previously we have generally said that you would be having a user defined specifications for your desired amplifier, right? So at that time you have only maximum undistorted amplification based requirement, right? So you could be having a requirement of the user for AC signal amplification as well. So we will do this inshallah time to time. So let's continue from here, right? So now we have left with these questions which are very easy to be answered once you have gone through all these previous lectures, right? So let's continue. We have seen that this could be a desired amplifier. A small AC signal at the base to emitter junction is actually superimposed on the DC voltage biased by this DC supply at the base to emitter junction, and they collectively give rise to a collector current, the collector signal current, the AC part of the collector current, which is also superimposed on the DC biased collector current. It means the DC bias collector current is because of this DC bias base to emitter voltage. And if you insert an AC base to emitter voltage, it actually superimposed on this DC biased voltage, right? That's what I called the AC about DC, right? So will be the collector current. We have a signal current against this input signal voltage at the collector, which is also about or superimposed at the DC biased connector, right? And we have seen that this phenomena graphically, right? This is what we have achieved for small signals. Otherwise, we would be having an exponential function here. So here you can see the AC collector current total is DC and AC part is this one, and which is nothing but the input base to emitter AC voltage multiplied by a factor which is purely our depending on our biased current and obviously the temperature in which we are working. So let's define this factor as GM. You know, with the Ohm's amplifier, you already knew that V is equal to IR, and 1 upon R is conductance, right? R is resistance, 1 upon R is conductance. So here GM is conductance, right? V is equal to 1 upon GM into I, right? So this would be called transconductance of this transistor, and its value is purely depending on your biased current, right? So we can rewrite this equation as IC plus GMVB. Instead of IC by VT, we can write GM. So graphically, GM, which is the transconductance of the BJT, is the slope of the ICVBE curve at the Q point, right? So it means for this input characteristics curve, you can also see this at the output, but currently we are having a relation with the collector current to the base to emitter voltage, right? So we are actually can show this kind of relation on input characteristics curve, right? So it means you have a transconductance of your BJT for the desired amplifier at the point where you have biased the transistor, the Q point, right? So for small signals, it means you will move your Q point with the insertion of a AC VBE to the characteristics curve of the BJT. Of course, load line is not shown here. Actually, the load line will move the whole transistor's Q point, right? For an inserted VBE, right? So it means graphically we can say that transconductance is nothing but the derivative or slope of the ICVBE curve at your Q point, right? At your Q point, right? And because this is usually a constant for a defined temperature, so GM is directly proportional to your desired, you are actually biased DC current, right? So again, from graphical representation as well, you can see that keeping the small signal amplitude sufficiently small, the AC signal amplitude, VBE will be very less than VT. For a small signal, input AC signal, this part of this AC signal which is becoming the AC VBE will be very less than the temperature based constant voltage. So operation is restricted to an almost linear segment of the ICVBE exponential curve. This was an exponential curve. This is an exponential curve basically. But for our operation for a small AC signal at this biased Q point, for example, we are in the linear region, right? So we can model it linearly, right? This line. Instead of taking this whole graph because we are working only in this region. So this region is what? This one, the previous one we have already biased, right? So thus the transistor is behaving as a voltage controlled current source or as a current controlled current source. What is the meaning? I will tell you. First, let complete this sentence. Understanding it will be explained later, right? Input port is base to emitter junction. Obviously, for common emitters, base is the input port with respect to the emitter, and the output port is the collector with respect to the emitter, right? You have a common emitter configuration, right? So then it means the last sentence means that transistor is behaving for this small AC signal for this biased current and voltage as a voltage controlled current source. It means we have at the output we have a current source value of which is controlled by a voltage, and or we have a current source at the output which would be controlled by an input current, right? Let's see how. This transistor is modeled like this according to this statement and as per our previous all discussion. How? Let's make a resemblance in these things what we have learned. And what is this? So currently just take for granted this sentence meaning and explain it here and show it here, right? So we have a current source at the collector to emitter junction, the output junction, right? And it is controlled by a voltage at the input port, which is the base to emitter junction, right? So it means we have a voltage control current source. It means the value of this AC collector current will be a factor multiplied by this input AC voltage at the base to emitter junction. So it means this value of this will be nothing but controlled by this voltage, because this would be constant once you have decided your Q point and once you have decided your operation, temperature of operation, right? So it means this is a voltage controlled current source. We can also say this